So welcome.
Well, good evening. My name is Bryan Bailey. So I have an interesting story. I'll tell my story quickly and then tell you what I do. Grew up in Buffalo Gap, went to Buffalo Gap High School, and was not a very good student. I'm just gonna be out right. I did. You know the kind, right? I'm not a troublemaker, but I'm kind of a rascal, and you know there's a difference, right? Yeah. But I did what was necessary to get through. That's about it. But I grew up with my dad, who's an electrical engineer, and he designed CNC equipment, CNC machines. And he's worked for what was then called Specialty Blades. And my whole childhood, he moonlighted for Specialty Blades. He worked at another company building custom CNC grinders for Pratt & Whitney, some of the bigger companies. But moonlighted doing design work, electrical design work for Specialty Blades, which is now called Cadence. And so I kind of grew up with this stuff. He says, well, I'll tell you what, son, I'll take you and your brother on a cruise and you boys help me wire the next machine. We were like, sure. And he had already taught us how to read his prints and everything and how to wire this stuff. So we're like, yeah, no problem, you know. So we're, I don't know, maybe 9 and 13. Wow. And this is our job, right? And put the wire label on. So his job was to put the wire label on. Mine was to run it, stick it in there, run it through the channel, and then go over to the drives or whatever I'm doing. So I had an interest in this, right? We also built a kit car from a 73 Ford Pinto. And yeah, I look like a Pinto anymore. That's the good part. So I really enjoyed the mechanical aspect of this. I also enjoyed the electrical aspect. So not very interested in school at all, unfortunately. But I knew I wanted to do engineering. So kind of a little bit of a disconnect. So I decided that I really didn't want to proceed with that. So I came to Blue Ridge. Probably the best test I'd ever taken was because I wasn't mature enough. You guys know what I'm talking about, right? The last 12 years I've taught auto mechanics at Grace Christian High School in Stanton, so I know the kind of kid I'm like, that's me. Bit of punk, kind of lazy. So I go to Blue Ridge and it helps me mature. It gets me kind of that way, and I have to learn how to study more and develop better skills. So I go here. And then I transfer to Old Dominion, and I go down there, and it was an experience. And by the time I got around to taking differential equations, it was all done, man. I unfortunately was not able to make it any further past my bachelor's degree. It's just not a chance for this guy. But through that, I had started working at Specialty Blades in my, on the weekends when I was in high school, and while I was going to school here, I'd work weekends and evenings and whatnot at Specialty Blades, running a machine or cleaning the floors or washing the windows. But when we were building a machine, I would build a machine because I had been doing that since I was a kid. Fast forward, I graduate, and I go back to Cadence, now Cadence, and they say, yeah, we'll give you a job. You have a lot of experience doing the machine stuff, and you've got a degree. So that's where I'm at. So at Cadence, I get to do some really awesome stuff. So I'll go through that in here. You had brought up before learning can be fun. So I've taught that learning can be fun for a number of years. Didn't teach this last summer. I teach automation, even the Panic robots in the team building, I guess it is.
Team building, yeah.
That's a lot of fun. I learned that I really love mechanical design and I love automation. So we'll get started here. The group I work in, it's kind of hard to describe exactly what we do, but our objective is to improve patient outcomes by developing and implementing innovative process technology. That's what we try to achieve. So basically, what makes us different from competitors, this is our large organizational point here. What we're trying to do is make medical device components for OEMs for new technology for medical devices. So I had my appendix out, and they do a laparoscopy. So now they can only do that with only 2 holes, and they use a tool that like a needle and a pair of pliers with a slot down the middle of it. And in that slot rides a blade, and while the blade is cutting, they basically clamp down the connective tissue while it's cutting. It's also driving titanium staples in both sides. So there's no suturing and there's no internal bleeding. And now that you're doing this, yeah, it's pretty exciting stuff. I didn't bring any videos like that. I used to not get excited about it, but now that I see the tools, I'm like, whoa, that's awesome. But anyway, so the connective tissue, they clamp down on it and it cuts and puts staples on both sides. So it's really fascinating stuff. So we make the blade and the, basically make the business end of it. We also make industrial blades for our hot dog and honey baked ham. You get a honey baked ham that has a spiral cut around it, think me. We put that spiral cut around that thing. Michelin Tire won't tell us what they're using our blades for. They're really secretive, so we have some companies that are like, I'm not exactly sure why. You know, that's all right. That's all right. So that's kind of where we're at. We don't make scalpels. So you can go buy scalpels by the bazillions for pennies each, kind of thing. We can't compete in that market. Scalpels are run to ground, and how you sharpen them is very, very preset. Everybody kind of knows them. Where we come in at is when you have a scalpel, but they want to use it in an MRI field. So we make it out of titanium, or we make it out of polycarbonate, or we make it out of a different material. So that's where we come in, is we've developed technology for that. So start cruising through here. I'll tell the whole thing and then forget to snap through this thing. So core competency, you guys get the idea here. Here are core competency. Here's where we, whoa, one too far. Here's where we start here is we made custom CNC grinders that are universal in their ability to be set up. So within a 2-hour time period, we can make a blade that's circular like a CD with an edge all the way around the outside. The next thing we could do is make something that looks like a bat wing. The thing after that could be a circular tube that's ground on the outside. So in-house, we know grinding. Grinding is relatively standard, but we try to configure the machines to be more universally set. So we can change it up. So if you'd like to have a blade that looks like a bat wing, we can manufacture that. If you'd like to have a blade that's 88 inches long and has a funny tooth design all the way down it, we can do that too. And it would be done on the same equipment. So it cuts down on all the different kinds of equipment we have there. So in that we discovered, well, we sure would like to have laser cutting. I'll get back to this EP here in a second. We love to have laser cutting in-house and heat treating. And one of our core competencies is making industrial blades, what we call like Oscar hot dog blade, and anything not for surgeons. So EP is an interesting story. Are any of you familiar with electropolishing as it's historically used? Are you familiar with plating, like chrome plating, how that would work? Electropolishing is simply the reverse of chrome plating. So instead of having a block of chromium in the tank and running it through a mixture of sulfuric acid and having the particles go from the block up to the surface, you flip it the other way around. Now your anode is your part, and the cathode is a plate in the bottom, a stainless plate. What we've done is we've developed a chemistry at a certain charge and time and temperature, and what we'll do is, get ahead of myself here, we'll take particles off the edge of the sharpened edge, and we'll basically, the particles will attract down to the cathode. So it's the reverse of plating, but we're the only ones that we know of that are actually electropolishing in this way. In little old Stanton, Virginia, right down the road over here. And there's a group of 8 of us. We're basically a bunch of country bumpkin kind of guys. We're all ornery in our own ways, and I'm into building custom motorcycles and stuff like that. And my friend's into building, performance cars. And other coworker started a landscaping company. And so all of us are kind of weird in our own things that we do. We all come together and we're trying to identify problems, right, and solve them in non-already existent ways. So that's where our electropolishing process comes from. That's why it's up there. Okay, so little history about sharpening an edge. When you see a sharpened edge, this is what you see. That's primarily what you see. This, we call that the grind. Then this is called the hone. And then there's actually a third facet at the end that you can't see. It's a little smaller than a human hair, and we call it a strop. You ever watch, you ever seen a barber sharpen? Yeah, you know what I'm talking about. Kind of keying up his blade on a leather belt.
Yep.
We have leather wheels. They're synthetic leather, but they're wheels in our grinders, and that is the last station. And we'll just kiss the edge, and it's just sharp as can be. So different geometry, double bevel, modified chisel, standard chisel. I don't want to bore you guys with this stuff, but basically this is how we're going to sharpen different edges based on whatever requirements you might have. Some examples of some of the stuff we make. These guys here that look pretty gnarly, those are for extrusion cutoff, so pipe and anything that comes out of an extruder will cut the length that way. These guys here are winder blades. I get excited about winder blades because they're meant for cutting like Oreo cookie film and really thin films that come off the roll. The rolls are typically like 88 inches long, and these things stand up and basically slice it. And then we have other blades that are called slitter blades that basically slit them to the discrete width, so you're left with a rectangle of film. And there's some ones on here, I don't remember what they are. I think, this one, I think, cuts the, when you buy mayonnaise, it's got that heat shrink wrap around the top of it. And yeah, you can thank me for that, yeah. And they basically, as they put that film around, they heat it, and right after it's in the heating process, this blade comes in, just slices the film, and then it heat shrinks the rest of the way around it. But they come to us, they shop with us, right? We're not the cheapest around, but we know how to make a keen edge, and we're willing to do it to whatever shape you want. That's kind of our primary objective here. Okay, so how do you sharpen an edge? These are grind wheels here. Have you ever ground anything on like a bench grinder, anything like that? Whenever you grind, you get what's called burr. And basically, it's the material that you plow out right down here. The roughness of your wheel digs in and plows the material, and it carries the material out to the edge. Now, it depends upon the hardness of your material. It'll either come off in just little teeny tiny particles, which is much more easily ground, or if it's soft, like 300 series stainless. We actually wind up digging into it and plowing it like you're plowing a field. So instead of particles coming off, they just kind of like, you just squirt them to the edge. So it's actually more difficult to grind a soft material than it is a harder material in our experience. But what you chase to the edge is burr. Now, before I was telling you about our electrochemical edge enhancement process, that's one of our methods to get rid of burr. And it's gotten us out of a bind in a number of ways, and it's won us many businesses because of that process. So we're not telling anybody how we're doing it. It's our secret sauce. We're going to ride that train. So speaking of secret sauces, this is a composite grind wheel here, ground or shaped in a conical form. And it does not run parallel. It's not constrained parallel to another wheel. Sorry, I'm getting ahead of myself. Let's finish this up here. To get it, and I talked about a double bevel edge where you have a sharp top and bottom. One of our methods for getting rid of burr and sharpening at the same time is we put the part on a fixture that sticks out here. It looks like this little duckbill thing. It sticks out here, and we basically plow it right in the knit point, is what we call that, in between the wheels. And how do we get the wheels to run together at the same time? You see how this has got like a thread, it's kind of got a curl shape through it? The wheel on the top has a right-hand thread, the wheel on the bottom has a left-hand thread, and they intertwine like this. So that they can be running at speed, and as long as they stay synchronized with each other, they'll never make contact. But you can see where my knuckles come together there's a knit point. So to change the angle of your ground edge, you simply open up the wheels or push them together, and it changes your included angle. So I had showed you before, there's the grind, as you can see, the hone was a much smaller angle in there. So we do that on 2 separate pairs of wheels. But the guy I work for said, hey, I got this idea. What if we tried to do that all with 1 set of wheels? So we take a couple of grind wheels, we bond them together, and then we shape them. And this was it. So it's actually kind of a taper. There's a slight taper to it, and it doesn't run parallel to the one on top. They actually run at a slight angle to each other. And we're putting the strip through it, and as it runs through, you're producing the grind, and then you produce the hone because you're inherently, your included angle changes. So mind-blowing. For me, I was like, can you do that again? Because I still don't follow you. The guy lives outside the box, and I love him for it. I really love him for it. And so he explains it to me again. I was like, one more time for me in the back, right? Can you do this one more time? And I get it. I'm like, oh. And he made this huge Excel spreadsheet, and he tried to figure out how this was all going to work. So we actually got a patent on it. We've got a couple of guys that have patents on a couple of things there. All in trying to solve a problem that we have in our little niche of the world. So here's a solid model. One of our grinders. I was showing you. I explained the page before. We had the two grind wheels that come together. There's one of the grind wheels. There's the other grind wheel. This is a 9-axis. So we have 3 stations where the wheels can move jointly or independently of each other. And then there's another station just like it, another one that you can't see behind here, for all the different grind wheels, and then we move the parts in and out of there. So all designed in-house and built in-house by us. You can't just go buy a grinder that we want, you know. So there it is, right there. There's the one that you saw the model of. We finished building this one here. I'll tell you something about these guys and ladies that run the machines. Dare I say they're artists? You know, generating a sharpened edge, there's no standard for sharpening. The closest we have is a cut force. So how much force is required to pierce said blade through such and such material? And that's the best we have. So we have customers that'll say, well, we're trying to cut the human eye, so here's some tissue type material, we want you to cut that, and we need it to be below whatever force. So we have a load cell, and we'll basically cut in multiple cuts and show them what we come up with and change the design based on that. These folks here, they know what they're doing, and they're good with trig, because you have to be pretty familiar with trig to get through this stuff. And I don't know, I like calling them artists because I think it's a pretty beautiful thing that they're done with, but I get excited about machines and blades and stuff, so, yeah. All right, so here's just some more drawings of, there's a picture of the actual tool, there's drawings of our tool, there's the blade. I was telling you before about doing laparoscopic surgery. That's the business end of that dude. There's the blade, that's what does all the cutting. So, stands about that tall. So top to bottom there is that tall. So we have a customer that is making end effectors for the Da Vinci robot, which is a frustrating name. It's actually not a robot in the least bit. Have you seen the Da Vinci surgical robot?
Nope.
The surgical robot is a misnomer. I get frustrated with this, but you know I didn't name it right. So the Da Vinci robot is simply really small end effectors with really small arms. And it looks like an octopus, it's got about 8 of them. And it's remote controlled. So the robot would be, if we're going to remove your gallbladder or something, now you don't even have to be inflated with gas as much because the arms are so small. And if your surgeon is a real big fan of caffeine, he's got the jitters all the time, you don't have to worry about that anymore. Okay? You don't have to worry about that because the Da Vinci robot is not going to have the jitters. Okay, so it's basically a remote control is what it is. But it's very small. So this thing here is huge. At the height of that is enormous compared to the end effectors we're now making for the Da Vinci robot, which do a similar thing, but of course it's got to be smaller. That's the frustrating thing in the medical world that we experience is everything has to be smaller than it was before. That's a problem because our fingers are only so small, right? The next one the one we're making for the Da Vinci robot stands probably about that tall, and it's got a little shoe on the bottom. It has a curved, sharpened edge in it. That bad boy is frustrating to hold on to say the least. Um,
How much does that bad boy cost?
this blade right here,
Yeah, what do you charge the customer for that?
what do we charge the customer for that? I think we charge $22 for the blade and the legs attached to it. The blade is actually designed to be steered around a corner. I like giving tours at Cadence. You all are welcome to come and give tours. And we have the tool there, and I say, look, it cuts this way, but wait, there's more. It goes around the corner, right? So if your gallbladder's kind of hiding out behind something, right? Just go in, turn the corner, and grab that bad boy and cut, right? So how we do that though is the blade must be actuated by a push rod. In our case, the push rod, they require to be 40 thousandths thick, so 0.040. The problem is 40 thousandths thick is kind of hard to bend, especially from the way the machine articulates in the tool. So what we've done is we've laminated 4 pieces of steel that are 10 thousandths thick, 010. And what it does, the laminate allows you to slip like this. So it's much more easy to bend. You still have the strength of the cross-section material. Just another fun thing, right? So, but how do you attach that, right? How do you attach 4 pieces of steel to the back of that thing? And by the way, that thing is it's 46 thousandths thick. So we're attaching 40 thousandths to 46 thousandths thick. We'll be laser welded because we discovered that's the best thing. So if you're familiar with welding at all, basically you're bringing 2 pieces of material together and you're trying to get at the joint for the material to go fluid locally to mold it together just in that one area. So we're not very good at welding. I'm not very good at TIG welding. So we use lasers because we can control them. So I'll talk more about lasers here shortly. I put this in thinking it would make some sense. It's just some fun talking points. Another interesting thing that happened is you guys familiar with the, words escaping me now. The bag, colostomy. It's gonna hurt, man, if I had to keep going. All right, the colostomy bags, patients with colostomy bags had no way to reverse that practically. And the company that had an idea for a way to reverse this, to recouple the bowel sections back together, they said, we need a blade that it looks like this. But the problem is, on this plane, across the surface, that cutting edge, has got to be as flat as possible. We haven't found anybody else that can make that flat. The reason why is, as you grind this facet around the edge here, you can imagine if you've got your tube here, and you're grinding with a ball wheel, basically along this edge, as you're grinding it, if the tube is not perfectly round, if it's kind of heart-shaped or has a teardrop shape to it, as you maintain that ball position, you're going to rotate and you're going to move. It'll basically the facet will move in and it'll move out and it'll be all wiggly. They were like, well, that can't be. But with the stainless we're working with, you can't make it that round. You just can't. So they said, you guys get 100% of the business because we haven't found anybody else willing to do it. If you could figure out a way to come through with this. So we're like, yeah. So, our group dynamics are like none I've ever seen. It's just how we work together. We have a respect for each other, and we definitely have heated discussions. We'll sit together for 6 hours or something like that, just drawing on paper and making little sketches and doodling things up, and taking what we know and trying to build on it and say, well, that idea is not going to work because of this, but what if we did this? You say, well, that's not going to work because you're kind of building off each other's ideas. So the solution for this was, I'm going to tell you guys the secret to our sauce, is we're measuring the outside diameter all the way around on quarter degree increments. And then we're recording that, and then we're moving the ball wheel in and out to maintain. So how we do that took a lot, but it's pretty precise movements, but it's able to get a flat plane across that top. It's pretty exciting. Let's see here. So a lot of our products are not our own creation. Almost all of them are not our own creation. We get them from requirements from a company that says, I need this made, I need this made, I want something that does this. It comes sometimes as crude as just a napkin with some doodlings on it, and then of course all the way up to finalized drawings with revision numbers and everything like that. These particular guys here are shavers. That's called a wrong thing. That's called a shaver. That's called a burr. If you have a cartilage issue in a joint, they're basically going to make a little teeny tiny hole, separate your joint a little bit, and put that bad boy in there, and it's just going to shave it right down. It'll shave bone, it'll shave cartilage, it'll shave whatever you want. Funny story, they use a thing called a hot dog test. How fast can one of those things eat a hot dog is kind of one of the measures of how good a product is. And the other thing they do with it is that they separate the tube, because it's a tube inside of a tube that will get like a pair of radial scissors. They'll separate them and count the particulate that comes out there. They call it shedding, as the material bears against the other material, which is a problem, right? If you have too much bearing because one tube is bent, the other one's not, this is a problem. So they came to us and they said, we need you guys to figure out how to weld dissimilar materials, for one, because these things down here are mighty hard. A lot of these things are used in ears, nose, and throat stuff. You want to be out when you see this bad boy coming. I'm just going to say that. So that's hard, but the tube that's welded to is, say, a 303 stainless tube. So we got to weld the two dissimilar materials together, but we also can't weld with any kind of, it has to be totally concentric, as concentric as we possibly can. Their spec, I believe, was I'm going to get it wrong, but I think it's 0.0004 inches. So considering a human hair is 0.004 to 006, they were like a whole order of magnitude smaller than human hair. Okay, challenge accepted. And there's one of the guys in our group, he's a tooling stamping guy to the nth degree, Mr. Detail, and he comes up with a way that we're going to constrain two spindles together. We're basically going to present the tip and the tube together. We're going to weld them together right there in that spot. So we did a lot of development work, and that was about, like 3 years of our time where we came up with it, and we were able to do it successfully to their spec. Yeah, I'm kind of already blue through that stuff. Okay, so here we go. My thing, all right? I love machines. I love automation. I love robots. So this is a Fanuc M1IA 4-axis robot. I nicknamed it Jellyfish. It kind of looks like a jellyfish. We got a bunch of these little jellyfish around there. So the previous slide where I was telling you we had that little tip. We're going to weld it to a tube. The tip is about that big in diameter and about that long. It's kind of bulbous on one end. When we pick it up and go to weld it to the tube, might be that long, might be that long, depends upon which product line they want us to be welding. And they wanted like 2.8 million a year. And so to have a person stand there, it's torture. It's punishment to have them pick it up, put it in the machine, close the door, hit the start cycle. Like 12 seconds later, it's done. Take it back out, and put a tip in there, to door, start cycle. It's painful. And really, it's not a good use of a person to do that. They're not happy with it. You're paying them a lot of money to stand there and do that. What's the best thing to do? The best thing is to automate. Our philosophy at Cadence is nobody ever gets fired because automation comes. We're going to use you for a more skilled role. You have these given abilities to do way more than just pick a part up and put it over here. So we're going to use automation. There he is, the jellyfish, put him on the table. So you see how it's got this little red backlight right here? How do you pick up randomly placed parts? Because these things come and we make them in a bag, and they're randomly placed. Instead of sorting them and trying to make them all go the same direction, which is kind of hard to do with a bulbous end on one end and open on the other, I said, why don't we just put it on this table here, and I'll use a camera, and I'll identify the profile, and after I identify the profile, I'll send the offset, where it is, and the rotation that it's at, back to the robot, and it'll just pick it up. So that was painful, but I got it to work. So there he is next to one of the machines we were building for doing this. That's actually a machine we bought and modified laser welding thing I was telling you about. You can't just go buy a machine that laser welds these things together like this, so we had to make it on our own. This is another automation project. Remember the legs I was telling you about for the linear cutter? I said we got to weld these 4 legs in the back of this bad boy. So we own a facility in Wisconsin that does stamping. We own a facility in Rhode Island that does a lot of machining. We own a facility in Pennsylvania that does final assembly work. We just bought a facility in Connecticut that does laser welding. We've been trying to vertically integrate ourselves a little bit more. So in Wisconsin, we have a stamping house. And the stamping house in Wisconsin stamps out those legs, 10 thousandths thick. So if we're making, what was it, 2.7 million a year, each one of those bad boys gets 4 legs, so we got a lot of legs. And what they had was a stamping press. And if you're familiar with the stamping press, basically it just stamps out the shape out of the material and barfs it on and down the road down here. They had people sitting there basically stacking them, because as we weld them, they all have to be in the correct orientation, and we like to have them stacked. So they had, I think it was 8 people sitting at a table. Their job was to take parts out of the bag and stack them up. They had to be about 350 on what we call a bayonet, which is just a plate of steel. And they said, can you come up here and see what we can do about this? I was like, sure. I've never been to Wisconsin when it's warm. I hear it's great, but I only go somewhere between November and March. That's like years running, that's when I go. I'm not sure why. But so I went up there and I was like, man, yeah, we can use some robots. We can get them doing this job. So this was my philosophy here. Jellyfish, another jellyfish, and this guy you can't see anymore, but there's a jellyfish. These are red backlights on a translucent belt. Basically, the stamping machine drops them onto this belt. The robot takes a picture of it, and then when it gets underneath the end effector, it tracks it, goes down, tracks it, activates suction on the bottom of it, and then stacks it onto a bayonet. So I have a little video I'll show you later of this guy actually running. So we don't have people doing that job anymore, but nobody gets laid off, nobody gets fired, nothing like that. They get to do something else. When they first saw me coming, they were like, oh, you're here to take my job. This one poor lady, she said, you're here to take my job. I was like, no, I'm not. Look, I'm not. I'm not here to take your job. I'm here to give you a better job. Do you really like doing that? Let's be honest. So anyway, long story short, it fills up, each one of these jellyfish fills up a bayonet, looks like this here. This guy's job is to go over and pick up the bayonet and stack it into this cleaning basket here, and then move the cleaning basket when it's full into here to put it in the cleaning machine, and then it picks up another empty basket and stacks it over there, and just kind of maintains itself. So an operator really only has to do anything with it every hour, maybe. Just make sure it has baskets. So here it is in real life. There's a stamping machine, and it just puts them on the belt, and they just cruise through. One of these 3 jellyfish picks them up. There's 3 of them because it comes out just that fast. I think they're 280 hits a minute, I think is what it's running at right now. And the stamping press can go faster, but the robots can only go this fast. I was like, how many robots do you want? I was like, well, we put 12 of them up here if we really want, but what makes sense? All right, I'll show you the videos later. What's our time look like? Okay, yeah, we'll hustle through. So these are some burrs that we make the blanks to. I was showing you before. We're going to weld these things in tubes for our customers. That's a machine we purchased, and we wrote programs for to make it on. Yeah, there you go. Laser welding. So the inside diameter, there you go. It's got to be concentric over here within 6/10. 0.006. So I was wrong. Not 0.004. So welding. We like laser cutting. We really enjoy lasers. We said, what the heck? Why not try some laser welding? And so we not me, another guy in our group. He's like our laser welding guy. We worked together on a couple of projects, but this here, basically, these are each laser optic heads, and this is universally set up, so we can put different parts in here for different things, and it basically presents it between the laser heads. That machine, I think, is 600 watt total, so 300 watt on either side, basically with fire, and it welds like right. Because when you think about all that energy being spot diameter laser welder is around 0.03 inches, I think. So there's a lot of energy through here. Okay. So there we are, where she's actually loading and unloading parts, welding here. So when we first got into laser welding the tips and the tubes together, we had this idea, we thought we really want to try this idea out before we actually commit to spending a year or whatever it's going to be designing a machine. So we bought this machine, which was I think like $80,000 for a machine. That's pretty cheap. So it was cheaper for us, think about that, it was cheaper for us to buy an $80,000 machine than it was for all of us engineers to design a machine, okay? We bought this, and we basically took all the stuff off of it and we outfitted it with lasers. So here's laser heads. And then these are independent slides, these are independent spindle heads. And we bring them together and weld them together with the machine. We try it out and we were like, hey, this actually works. The machine didn't have any way to align the spindles together, there's no adjustment. So my friend and I, what he would do is we made a little tool that would allow us to index the spindles together to see how not parallel and not concentric they were. And I ran around with a wrench and I adjusted the base of the machine to get it to twist one way or the other, just to kind of get that bad boy to sneak it in a little bit. And we got it pretty close.
Like your washing machine.
Yeah, exactly. It was not 0.004 inches. I'm just going to leave it there with that, but it was better than what it was. Okay. So we like leading robots to welding together. They suit each other very nicely. This is another welder that we were working on designing. So to give you some scale, this is what we're welding, and this is a penny. So these are our weld lines. We can weld radially. We can weld dissimilar materials. Yeah. So everybody's trying to get small, so we're trying to get small with them. So this was our concept for how we're going to actually weld it together before I showed you the slide of the machine, added twist base and everything. This was our concept once we learned from that machine what we were going to do. This was kind of like our, we shot for the moon, and then we had to kind of bring it back to reality a little bit, so it doesn't quite look like this. This was our dream. Yeah. Here's the reality. It's still got that triangular stability housing to it, but it's actually laying horizontally. Laser optics in there. So we're doing the welding. There's the business end right there. There's some feed tubes into this hopper. So the interesting thing, you guys are teaching, you share with students. You get locked in your mind with a certain idea. You just can't get out of it, and you just feel like, well, that's it. You just can't do it. But you know, failure really isn't an option, and especially if you get paid for it, it's really not an option. So, this little thing has a fun story with it. I could not figure out how to feed tubes up the back of the spindle and have them come out singulated and push them off the spindle and everything. So we went to the little Mexican restaurant down the road from where I work, and they had one of those little toothpick dispensers. I rolled out to get a toothpick. I was like, wait a minute. So that's a toothpick dispenser. It's highly modified, but it's a toothpick dispenser. What I found playing with it was all the toothpicks on my little tubes kind of made an arch, you know, around the drum, the rotating drum that I was using to feed it. So I had to have little exciter bars that would go up and like, you know, aggravate the stack and make them all fall, and then fall right down in there. I was like, you know, inspiration comes from everywhere, doesn't it? So I stole somebody else's idea, and that's fine. So this is a concept I had where we were going to weld with a robot, because how exciting would that be? It turns out the robot's got a little bit of the caffeine wiggles at its extent, so it wasn't the precision we were looking for. This was my idea to try to come up with that. Some final thoughts for you guys. Innovation is more about discipline than creativity. It is creativity, right? You have to see the next picture. How do you know what the frame looks like on your next picture? You have to know where you're at. You have to know what exists to be able to drive to the next place. So before you start trying to paint in what it looks like, you really do need to have that frame. You need to know where you're going and have a general idea of where you came from. So in my mind, it's about disciplining yourself with what you know, what you can find, and then taking that building on and going to the next step. Successful innovation builds incrementally on existing knowledge. That's basically the same thing you said. Our success is driven by employees with diverse complementary technical skills. That's a nice way of saying, I viewed engineers as, managing engineers has got to be like herding cats. Because an engineer knows a lot about one little silo of something. But you feel like you know a lot about a lot then. So you have an opinion about everything, right? So I'll just leave it with that. So, but we do work well together, a lot of us. Each one of our skills, the laser welding guy, when I have welding issues or questions, I'm like, dude, hey, you know, let's talk together, let's brainstorm, let's talk. I want your input because I don't know, and vice versa. And my dad, I think I brought that in. My dad had done a lot of design work. He just retired last year. He's done the electrical design work on machines that I've designed and everything. So we've had this fun relationship working together for a long time. Strong team and interpersonal behaviors, and then iron sharpens iron type relationship, as I was alluding to before. You know, I'm learning from the other guy, and he's learning from me, and we're going to try to bounce off of things with each other. We may disagree, but that's okay. It's part of our relationship. Demonstrated ability for continuous learning. A lot of the employees at Cadence, that's the big requirement. You want to come work for Cadence, you don't have to know how to make the brain tumor extractor thing that we were working on in this project, because we don't really know, right? I mean, we just know what we know, but we'll tell you that. But what we really want you to do, what we want you to bring to the table, is a drive to learn and an understanding that we're all working together in this. Not that you have to come to the table and we have an expectation that you know this, and if you don't, we're disappointed. We've seen a lot of employees show up and they want us to think that they don't need to be taught. We're like, a lot of our equipment here is just here. We don't expect you to know, but what we expect you to bring to the table is the ability to learn and drive to learn. So I'll pass through this stuff and say speed here. Are the videos?
Yeah, I put a text file.
All right, let's see if I can do this here. You gonna let me do it? Come on, you can win here. There we go. It's just a bunch of machine noise you hear in the background there. But this was the one I was telling you about in Wisconsin. These are the little parts that are being stamped, and the robot is just tracking them, picking them up. Now you see this guy's missing them. That's because it's going to get out of his field of operation pretty quick. So he knows that. I say he knows that he's a program. Robots are dumber than bots. I spent a lot of time programming a lot of smarts into this stuff. So this guy has almost nothing to do. Right? He's just kind of hanging out. Every once in a while he gets some of the scraps from the first two. This guy's job is just to pick up a full bayonet. You see this bayonet right here is already full. Once it's full, the robot shuttles this slide over and exposes a fresh, empty bayonet, and then signals a bit to this robot, hey, come get it, it's full. So that's what this guy's doing, is he's fishing it out of there. I like robots that move in like ballet moves. So there's a little bit of like sliding kind of motion to them. I think it looks way cooler. And with this guy, speed wasn't the objective, so that's his job. Lots of little nuances that you basically have to fight your way through as you're doing something like this. These little bayonets, these steel plates, all of them have a certain amount of bend to them. And the robot's looking, it's got to be right on to drop it on there and make it stay. So I used a laser distance probe, and it just gives me a discrete value, and then I do some math inside the robot control, and then the robot knows to move, 0.1 millimeters this way for this bayonet, and then after the robot swaps it out, the next one it measures that one, and that's how it figures it out. So here's coming to get an empty basket, put it over there where he can load it. This was a hard move. I kind of painted myself into a corner. The enclosure is really tight. Yeah, I wanted that to be a little bit more of a suave move. But when you're stumbling around in the dark looking for the bathroom door, sometimes you just fumble around. That guy's fumbling around. So he's picking up an empty bayonet and moving on with it. So he's checking presence to make sure the bayonet exists, and he's gonna, I'll leave the, here you go. Got one more little snazzy move. They give me a hard time sometimes about it, but. Okay, one more. Do we have time for one more, or should we quit?
No, it's, we can watch it.
It's only a few minutes here.
No, plus the videos really make it.
Yeah, there you go. So the videos are fun. Come on, no ad, no ad. All right. Yeah, so we got to start in the beginning here. So this guy's job, make a blade, or it's not even a blade, it's an assembly called a staple remover. And it's for removing staples for facial surgery. So you can't have tear out. You can't have any tear out of the flesh. The staple has to come out exactly the same path it went in. So this particular assembly here has a mechanism that basically bends the staple of that particular size. We make a whole lot of these things, and in this case here, it's just all we're doing is taking the blanks, one upper and lower, and we're injection molding the handle. That's all we're doing here. Nothing secretive here at all. But the people they had running this, they would have one person run it for about 2 hours, and then they would cycle that person out, put another person in there, because it was just exhausting for the person to stand there and fish out the parts, and then put them in here. When it swings back around, they'd take these parts out, hang them up over here, go over here, get more, and their cycle time as their shift would go would just drop. So this robot moves slower than a person does. A person can go a lot faster, and that's typical for what I've found in automation is a person can go very fast, but for a brief amount of time. Whereas the robot just continually does the same thing. He doesn't have to go to the bathroom, he doesn't get hungry, he doesn't have to call his mom. He's always there. And it'll continue to do it for both shifts. You don't have to pay for a second shift person as well. So he's just taking it out of the molds, putting it in this basket over here. The basket just fully rotates the basket around, and an employee has to empty it out. So loading them in there, so there's an interface with the machine. Did the parts actually get into the pockets? Yes, then proceed. In this case here, found an upside down part. I had to add that thing later, that's a fun story. I thought I would be able to bump the bottom of the table, these little shaker tables we made. Like you bump the bottom of the table, the parts would flip over. Nope. Nope. I mean, if you bump and bump and bump and bump and bump them until you're like, really? Eventually somebody flips over. You know, then you gotta do it all over again for more parts. Just not appropriate. So I set him up to see the other part right side up and upside down, and picks up an upside down part and puts it in that little rotary flipper, flips it, and picks it up right side up. Yep. So yeah, interesting stuff with robots. This guy's actually running 4 programs at one time in parallel, pinging vision and moving the tables accordingly while the robot's in motion, not in the field of view with the cameras, 2 cameras running in there. So.
Is this at your facility in Stanton?
This one's in Wisconsin.
That's in Wisconsin.
But I like cold. Yep.